Hello and a very warm welcome to EPD640, an introduction to polymer rheology. My name's Bart and I'm going to be your instructor for this course. To start with, I'd like to give you some motivation for studying this fascinating subject and show you how rheology matters in products used by everyone every day. I'm also going to give you an outline of the course, introduce the format of the lessons and some of the assessments, and also give you an overview of the learning objectives. So let's start, however, about the course, and specifically this embodiment of the course. And the embodiment of the course that you're about to receive is one that is derived from a course that was taught at the University of Cambridge in the UK for very many years. So for those of you who don't know the UK or Cambridge that well, there is one of the iconic photographs of the River Cam and the Backs, as they are called, and of King's College, Cambridge, which is one of 30-odd constituent colleges that make up the university. So for those of you who might watch carols from King's on Christmas Eve, which is broadcast worldwide, that is King's in the summer. Very, very nice indeed. Very pleasant going punting along the Cam. So Cambridge is situated in the eastern part of the UK. It's rather flat. It can get rather wet and it can get rather windy. But it's a very, very beautiful area. And that's currently where I'm based as well. So for all the online work that we'll be doing live together, there's going to be a little bit of a time lag because it's going to be quite late in the evening where I'm based. So rheology has been taught at the Department of Chemical Engineering, latterly the Department of Chemical Engineering and Biotechnology at Cambridge, for a very, very long time. And it's all thanks to this chap here, Professor Malcolm Mackley. Now, Malcolm introduced rheology to the Department of Chemical Engineering, as was, in the early 1980s. And his vision was an excellent one, because rheology can be a very mathematical subject. Sometimes it's very important to have a very high level of mathematics to describe some of the more complex phenomena that goes on. But rheology also can be understood by looking at the physics of what's going on and understanding physical principles. So Malcolm's vision was to try and communicate as effectively as possible the physical principles that are important for rheology, whilst keeping the mathematics to just an essential minimum. And that is something that I'm going to try and do on this course as well. So Malcolm taught this course, or a derivation of this course, a forerunner to this course, up until about 2008. I then took the course over. I was one of Malcolm's PhD students in the early 2000s, and I co-taught the rheology course at the University of Cambridge with a good friend and colleague here, Professor Ian Wilson, for a period of about 10 years. And we co-taught this course. I used to teach the general introduction with the viscoelasticity. Professor Wilson used to cover the viscoplastic and suspension rheology side of the course. And so what I've done for the University of Wisconsin is to distill and extend the basic introduction to rheology, which is all around equations of motion and examining stress and constitutive equations, and also polymer viscoelasticity. So, before we get any further, it's probably worth exploring what rheology actually is by definition. So, if you were to go to a dictionary or an encyclopedia, you'd probably see a definition along these lines. So, rheology is that branch of science that deals with the deformation and flow of matter, in particular the non-Newtonian flow of liquids and the plastic flow of solids. Rheology is a division of the broader field of hydrodynamics. That's a very, very broad definition indeed. The deformation and flow of matter, that's basically fluid mechanics when you look at it in terms of liquids, or solid mechanics when you look at it in terms of solids. So it's a very, very broad subject, and as such, we're going to be focusing on just one facet of the subject for this course. If it's a subject you wish to explore further, there's many, many avenues that you can actually go down. So the word rheology has been in use for almost 100 years. I'm making this video at the end of 2023. So 94 years ago, Eugene Bingham, in the Proceedings of the American Society of Testing of Materials, coined the term rheology. And apparently, if one was to read this journal, the subject under discussion was designated as the science of the deformation of matter is rather cumbersome. And it doesn't exactly trip off the tongue, the science of the deformation of matter. So a large number of words have been suggested, and John R. Crawford, late professor of Latin at Lafayette College, inclined to the belief that rheology is the most appropriate designation, and therefore this term will be used for convenience in what follows. Not only has that term been used for convenience in what follows in this particular paper dated in 1929, it has actually withstood the test of time, because almost a century later, rheology is a very, very well-established subject, and the term is understood globally by those who practice it. So we're going to be looking at deformation and flow. We're going to be looking firstly at Newtonian liquids and then non-Newtonian liquids. Non-Newtonian can take many, many different forms. It can mean mild deviations from Newtonian behaviour, or it can mean completely different sets of physics in addition to Newtonian behaviour. But I'm getting ahead of myself. A lot more about that later on. Let's have a look how rheology impacts things that you know about. Let's think, for example, about paint. Let's say that you're repainting a wall in a house or repainting a ceiling in particular, and the idea of the paint, as well as to cover up the wall and look nice, is basically not to fall off the wall. But we want to get it on the wall in the first place. And so there seems to be this essential dichotomy, because you need to get the paint on a brush or a roller or a paint pad, and you don't want to really fight the paint to get it on the brush, roller or paint pad. Then we want to apply the paint to the wall in such a manner that we can get a nice surface finish. So again, we don't want to be struggling getting the paint off the brush or off the roller or off the paint pad. And then once the paint's on the wall, we really want it to stay there. We don't want it to flow down the wall or drip off the ceiling. So if we think about that problem, we can see that actually the paint has to behave in slightly different ways depending what we're doing. Ideally, we want to get it on the brush nice and easily, and so we got a high deformation rate when we scrape the brush in the paint in the tin, and at those high deformation rates we want the paint to be nice and fluid. Likewise, when we're applying the paint to the wall with a brush or a pad or a roller, there's potentially high deformation rates of that fluid going on, and again we want the fluid to flow nice and easily. However, when the paint's just lying on the wall, there's no applied deformation. It can drain under gravity, which itself will apply a deformation force, but at those low rates of deformation, we don't want the paint to do anything. We don't want it to flow. So we can tailor the rheology of the paint, its response to deformation, in order to get those product qualities. Let's think about another example. Let's think about an article of homeware. For example, I don't know, some plastic cups. These might well be injection moulded, and we want to make sure that the thermoplastic with which we use to make these materials is reliable when it's injection moulded. We might have a polypropylene, for example, that we squeeze under very high pressure into a mould, and that mould is shaped like a cup. We want the material to fill that mould. We want that material to behave in a predictable manner when it enters that mould. We want the material not to shrink too much when it cools down, and we want to make sure that there's no residual stress within the material that can give rise to premature failure of that product later on in its life cycle. So, in order to understand the stress behaviour of such a material and its flow behaviour of such a material, we need to be able to understand how the molecular architecture of the polymer affects the flow, affects stress storage, and then how that stress is then released, and then make a judgment as to whether or not those stresses are going to be retained residual stresses in the product, possibly leading to problems later on, or not. These mugs could also be made of china clay, and so we have a completely different problem, but one that's still rheological in nature. We may wish to shape form a mug in a traditional way on a potter's wheel, and we may get our lump of clay, we throw it onto the wheel, and we start to make a mug. Great. However, when we've got the wheel turning, we want to be able to form that mug, maybe with our hands, because we're doing this the old school way, and when we're doing that, the material is deforming and flowing. However, when we stop applying our hands onto the rotating clay, we don't want the clay to sag back down into the shape from whence it came. So what we want here is a material with a fairly high yield stress, but the material that can flow once that yield stress has been exceeded, but what doesn't flow once that yield stress isn't exceeded. And again, the subject and science of rheology can help us understand that behaviour and design these materials. Let's move on to something that's probably close to everybody's heart, which is food. A lot of food processing operations are done on a very, very large scale, simply because there's very large demand for it. So if we were to look at, say, the manufacture of some breakfast cereals, the way in which they're manufactured looks a little bit like a polymer processing operation. You'd have some derivative of, say, starch. It might be a starch melt, it might be a starch solution that we wish to shape form. Extrusion is a very good method of shape forming, and so we'll extrude this starch melt or these starch solutions or starch derivatives through a set of extrusion die that'll then go through cutters and then goes through some process to ensure that that shape is retained. So the science and engineering behind extrusion is an absolutely fascinating one, and one that you'll probably see in a polymer processing course, but understanding how the fluid behaves in an extruder is very much the science of rheology. Because if we look how fluids flow and deform through that extrusion line, the stresses are subjected to and the stresses that they may store if they're viscoelastic in nature, the whole goal of the extrusion line is to shape form. So what we want is a predictable, reliable shape to be made by this process, and the properties of the material will largely designate whether that shape gets made or not, because some polymers will deform horribly after shape forming to produce something that bears no resemblance whatsoever to the shape through the die from whence it came. So understanding the rheological response of molten polymeric materials, be that petrochemical-based polymer or food-based polymer or biopolymer, is actually very, very important when we come to do shape-forming operations with these materials. Let's think about a fascinating industry as well that's growing very, very fast and diversifying into many, many different application areas, inkjet printing. Most of you will be familiar with inkjet printers in your home office and how they're incredibly fast, incredibly high resolution devices these days. But if you think about the science and technology of ink design, how you get an ink to jet from a piezo-based or a thermally based printhead onto a piece of paper in a very predictable, incredibly repeatable, consistent manner, because during the course of one print you're probably ejecting millions of droplets, and each droplet has to behave in exactly the same way, you'll see that actually how you design the ink and how you quality control the ink is going to be incredibly important. And in order to print at the high speeds that you see today, you have to have a degree of elasticity in the ink in order to stabilize it. And so how you formulate the ink, how you add that degree of stabilization via tailoring the ink's rheology, the viscoelasticity in particular, is an incredibly important part of how inkjet printing works in the first place. If it wasn't for thorough understanding of ink rheology, inkjet printing simply wouldn't work. End of. So we're going to be dealing with some very, very interesting materials. We're going to have materials that have got properties of viscosity, properties of elasticity, sometimes properties of plasticity. And these complex liquids can display some very, very counterintuitive behavior. And one of the objects of this first lesson is to introduce you to some of this unexplained flow phenomena that you obtain. So, for example, some liquids can actually flow against gravity because of a build-up of stress in them, giving them enough body force to flow against the body forces imposed by gravity. These liquids can also what's known as self-pour or self-siphon, which is an interesting problem, especially if you're a chemical engineer, especially if you're trying to design maybe, overflows to tanks. If you have a tank with a viscoelastic liquid in with an overflow, if that overflow is breached and you get a little bit of overflow, but it keeps outflowing even though the liquid level in the tank is below the level of the overflow, which can happen with self-pouring liquids, then you probably need to know about it. Other rheologically interesting materials can sometimes behave like elastic solids, but at other times behave like viscous liquids. Silly putty, for example. If you get silly putty and roll it up in a ball and throw that ball at a wall, it'll behave like a rubber ball. However, if you get that silly putty and leave it on a desk and come back an hour later, it will have formed a pool. And so you've got elastic behaviour at high deformation rate and viscous behaviour at low deformation rate. Back to the paint problem. Liquid viscosities can change with deformation rate and time. So there's sometimes a need to have low viscosities at high deformation rates. Think about painting a wall. You want the paint to go on nice and easily, you want it to flow. But you want very, very high viscosities at low deformation rates, or at long times after it's been applied to a wall. And so you've got these interesting behaviours where material properties change as a function of deformation rate and as a function of time. When we were talking about extruding breakfast cereals, I alluded to the fact that some materials can distort unrecognisably during shape forming, something that we call dye swell or extradate swell. And so we need to understand why this happens, and it's all down to retained stress in the material and how those stresses relax, because stresses will cause flows, and sometimes those flows end up completely destroying the shape forming that we've just done. One of the really fascinating phenomena that was discovered relatively recently, within the last 20 or so years, was that elastic liquids can also exhibit something that looks very much like chaotic turbulence in flow regimes where you absolutely would not expect turbulence. For those of you who have been on fluid mechanics courses before, you'd usually expect turbulence to be linked to flow inertia and high Reynolds numbers. But you can get chaotic turbulence that's viscoelastic in nature at vanishingly small Reynolds number. And so we need to be aware of these unexpected flow phenomena, and we need to be able to understand these unexpected flow phenomena as well. And that is where a good understanding of rheology can be a very, very great help. So let's think about rheology in the industrial context and in professional practice. So it's a very, very broad subject, as I've said already, and contains many different branches. I'm only going to illustrate two here, but I want to make a particular point. Let's say what you're doing is designing some materials processing equipment. It might be for shape-forming breakfast cereal, let's just say. What we want to do is to make a consistent, high-quality manufactured product, and we want that consistency not to be just hour in, hour out, or day in, day out, but we want it to be year in, year out, because the consumer expects the same product every time they open that packet of breakfast cereal. And so in order to do that, we need to understand the process that makes that shape forming very, very well. So almost certainly there'll be a lot of design work that goes into that, probably some modelling work that goes into that, maybe even some innovation and R&D work that goes into that, to try and develop a core of scientific and engineering understanding that allows us to control the quality of that manufactured product. However, we can't just focus on the materials processing operation alone. We have to think about the fluid that goes through it. So it might be a starch melt or a starch solution, and we need to understand what the characteristics of that material are. So we need to understand the fluid response as well as the process response. And in addition to modelling the process, we need to understand how that liquid can be represented by a model as well, because we want to make sure, month in, month out, year in, year out, that the fingerprint of that liquid is the same every time that we use it. We might, for example, get different batches of material, raw material coming into the process. We want to make sure that whatever we make with that raw material can be shape formed in the same way, and that we can compare a new batch of material coming in that we don't know its behaviour of to a batch that we know works. And so getting the analysis tools and the analysis methods to a point where we understand them well enough to do that will allow us to ensure good quality control of our materials, which in turn will ensure good consistency of our process, and those two combined will lead to the good quality of manufactured products. Let's think about rheology in the broad sense of fluid mechanics now. Some of you will have sat on fluid mechanics courses before, others of you won't. But for those of you who have, you'll be familiar with the concept of Newtonian fluids and non-Newtonian fluids to a point, and the concept of Reynolds number. For those of you who haven't sat on fluid mechanics courses before, don't worry. Newtonian fluids are the simplest possible fluid that we can describe. Reynolds number is a measure of inertia. Basically, it separates very straightforward flow phenomena, laminar flow, from very complex flow phenomena, turbulent flow. And so nice simple fluid mechanics problems are where you have Newtonian fluids and laminar flow, and we'll be examining these in the lessons that come. And we can work out relatively easily things like flow profiles and pressure profiles. When we're dealing with Newtonian fluids in turbulent flow at high Reynolds number, life gets a bit more tricky. Let's just put it that way. So we'll be seeing a little bit on this course things to do with creeping flow, things to do with the Navier-Stokes equations, and we'll be ensuring that we understand the origin of these equations. We'll be doing a lot of revision around this to make sure that the base on which we're building has indeed got very, very solid foundations. We're not going to be thinking about turbulent flow of Newtonian fluids. This is a complex area that needs a dedicated course in its own right, and this course is not that. But again, for those of you who are familiar with fluid mechanics, you'll probably recognise that there aren't that many analytical solutions out there. You're going to be doing a lot of computational work, and that turbulence modelling in computational fluid mechanics can require a lot of experimental validation in order to make sure that you've actually got answers you can rely on. So we've gone on this axis from creeping flow Newtonian fluids, nice and easy to analyse, through to chaotic turbulent flow, high inertial flow of Newtonian fluids, which is really hard, but is done routinely using elegant computer software. Let's think about the non-Newtonian domain. We can make an analogy. We can look at the non-Newtonian analogy to creeping flow. We can look at simple flow geometries. We can look at simple rheologies, and we can use this to get a good physical understanding of the subject and a good physical understanding of the phenomena that lead to complexity. And that complexity can be made analogous to turbulent flow in Newtonian fluids. Turbulent flow in non-Newtonian fluids is incredibly challenging. It's a research topic. It's still very much ongoing, both in terms of fundamental physics and in numerical methods. So, what we're going to be concerning ourselves with are things on the left-hand side of this diagram. Analytical solutions for simple geometries and simple rheologies to gain insight and understanding. We will also be doing quite a lot of revision on Newtonian fluids and creeping flow as well, because one is a complement to the other. So let me now give you an overview of what this course is going to contain and how it's structured. The course is structured in two parts: pre-midterm, post-midterm, the midterms being a nice divisor. So part one is all around key concepts, Newtonian fluids and generalised Newtonian fluids, and there's 8 lessons in part one. This is the first lesson. It's basically just an introduction to rheology, to some basic physical principles, and also to a teaser to make you understand some of the more interesting flow phenomena that we obtain in rheologically complex liquids. Second lesson is going to be a mathematics survival guide. I appreciate that you all have different backgrounds and that mathematics can be a fairly varied background knowledge. So I want to give you the essential bare bones of some vector calculus, some matrix operations, some complex numbers, some differential equations that we're going to be using throughout this course. So hopefully that will give you enough revision or enough introduction to the mathematics that we'll be using. I'm then going to talk in lesson 3 about stress and about strain rate, and about how we link these two together, because stress is important, because this is actions of forces on fluids, and if you act with a force on something, it tends to move, and when it moves, fluids can deform, and that's described by strain rate. So we're going to look at these two basic descriptors of flow. We're then going to build on that in lesson 4 and look how we can use these quantities in describing how fluids flow. And we're going to derive some equations of motion that allow us to describe how fluids flow. We're then going to go in lesson 5 to look at some flows of Newtonian fluids, with a focus on those flows that are used in tools that uncover the rheology of a material. So we're going to look at rheometric flows. We're going to look at flows in capillaries and flows in between rotating cylinders, which we call Couette cells. We're then going to generalize this a little bit in lesson 6. Up until this point, we've been dealing with Newtonian fluids, which are the most straightforward fluid to analyze. And I want to take one step away from the Newtonian fluid and talk about something called a generalized Newtonian fluid. It's the simplest deviation we can make from Newtonian behavior. I'd then like to talk about some measurement methods, because when we're talking about rheometric flows, we're talking about those sorts of flow scenarios that are used in measurement techniques. So it then makes sense to talk about those measurement techniques whilst the flow scenarios are nice and fresh. And so I'm going to talk about rotational rheometry, capillary rheometry, and in lesson 8, extensional rheometry. So that is part 1 of the course. Part 2, after the midterms, is all around viscoelasticity. Now, these are fluids that have both viscous behavior and elastic behavior. And this is where things get really interesting. So we're going to start by looking how we describe the phenomenon of viscoelasticity in a way that I hope will allow you to create some good mental models and understanding. So we're going to be talking about something called linear viscoelasticity at first, and one of the models that can be used to describe this, the differential Maxwell model. We're then going to explore how we use this differential Maxwell model, which is a very simple descriptor, which doesn't necessarily capture all the effects that we see in real materials, and we're going to develop it such that we can start to use it to describe the behavior of real materials. And so lesson 10 will describe how we convert it to a different mathematical form such that we can then put extra physics into it. And then lesson 11 puts the extra physics into it such that we can say, for example, match the behavior of molten thermoplastics, a thermoplastic starch, or a thermoplastic such as polyethylene or polypropylene. We're then going to look in lesson 12 how we extend these descriptions even further. And this is going to be a very short and brief introduction to an area called convective constitutive equations. And these are mathematically quite complex, so this will only serve as a basic introduction, but it will give you, if you like, some insight into how we can use the physical basis of what we're talking about in models that can then be solved computationally. We're not going to do any computational rheology, but at least if you do go down that route in the future, you'll understand where the models that are solved actually come from. In lesson 13, we're going to look specifically at polymer solutions. The material that we'll have covered up to that point can be applied to either polymer melts or polymer solutions, anything that has the property of viscoelasticity. But polymer solutions are quite interesting in their own right. So again, it's going to be a brief introduction, just one lesson, to the fascinating topic of polymer solution rheology. Lesson 14, I'm going to give you 3 examples of how to characterize fluids, some worked examples. So hopefully this will be of use to you when you come to do fluids characterization for yourselves. Lesson 15 will serve just to round the course off and summarize some of the key points that we'll have made over the entire 2 parts. So the way the course is going to be organized is each lesson is broken into between roughly 3 and 6 parts. Each part is about a particular topic or a particular subtopic, and a video of each part will be on YouTube. So hopefully these videos will be one of the useful instructional media through which you can learn about the subject. Now, some of the videos that you'll see are videos that I put together for the course I used to teach at Cambridge during the pandemic times. So when I'm looking a little bit younger and a little bit less tired, those videos are a little bit older. And I make an apology here because the organisation of the lectures at Cambridge are different to the organisation that I've put together for this course. And so sometimes one of the video introductions will say, welcome to lecture 5. And you go, this isn't lecture 5, this is lesson 3. So please ignore that lecture number. For this course, it is not relevant. But the content of those materials, however, is very relevant. So if you're willing to overlook the lecture number at the beginning, hopefully you'll find the rest very, very useful. The videos where I'm looking slightly older and slightly more haggard are ones that I've made specifically for this course, and they do have the right lesson number. So I'll leave it for you to spot which is which. So lecture notes for each part of this course are going to be made available at the start of either semester for part A or after the midterms for part B. So you'll have 130, 140 pages of lecture notes that accompany the videos specifically, that contain all the key points and the explanation. So hopefully with a combination of both video work and lecture notes, there's a good body of knowledge there to serve as a foundation for your learning. There's going to be some homework tasks to embed the knowledge that we're going to be talking about as well. And I'm going to try where possible to relate these homework tasks to polymer processing type operations. It won't always be possible to do that, but I'll endeavour to do my best. So the idea here is that you can apply the knowledge that we're accruing to solving polymer processing type problems and polymer engineering-y type problems. So hopefully these could be useful illustrators for you as you go in your professional career to apply the knowledge that you're going to learn on this course. So there's 6 homework tasks for part A and 5 homework tasks for part B. Now, in terms of assessments, these are liable to change year on year, so I'm not going to describe them here because I'm hoping this video material is relatively evergreen in terms of its content, but details of the assessments and their timings will be given in the course documentation, and so I'm going to leave you to refer to that to get more details for those. So finally, there's going to be 1 live web meeting per week. As I mentioned, those web meetings will be held after work for you, most likely, which means that for me it's going to be very late at night, so apologies in advance if I look a little bit tired. I will almost certainly put a shared document online before these meetings, such that if you've got any specific questions, you can put them in that shared document, so other people can see that topic's been asked about, and I also get some preparation time in advance such that we can make the best use of that 1 live web meeting, which will be limited to an hour. And so if you're willing to put questions there in advance, that's great. Otherwise, what I will do in these sessions is go through homeworks and homework solutions and give you an example of what it was that I was trying to convey in terms of learning in those exercises. So let's have a look at some learning outcomes. So the first learning outcome, hopefully, is to be able to describe and understand the difference between Newtonian fluids and non-Newtonian fluids and how we deal with them. A second learning outcome is all around the mathematics of continuum mechanics. Continuum mechanics is the sort of the physical subject underpins fluid mechanics, and so when we're looking at, for example, applying Newton's second law to a continuum fluid, we do it in a slightly different way than we would if we're doing it for a point solid. And so a second outcome of this course is that you should be able to use those mathematics, be able to solve the Navier-Stokes equations, be able to understand tensors, for example, and use them to solve problems. The third part of our learning outcome set is that I'd like you to be able to apply a constitutive equation, which is an equation that links strain rate to stress, to analyse non-Newtonian phenomena which is exhibited by polymeric fluids. And we'll see all to do with this on the second part of the course. What I'd also like as an outcome is for you to be able to have a toolkit to investigate real flow processes that involve polymer solutions or polymer melts, be they shape-forming processes, be they understanding how pressure drops vary down a conveying line when you've got a shear thinning liquid, maybe understanding the flow patterns in a concentric annular blow moulding die, or something of that nature. And so you'll be able to put into practice some of the basics that you've learnt on this course to start to give insight into those engineering applications. Also, an important outcome of this course is fluids characterization. If you've got an unknown fluid, I would hope that by the end of this course you'd be able to say to yourself, yes, fine, I know how I'm going to characterize this fluid, and I know what I'm looking for in those results to determine whether this is a Newtonian fluid or a non-Newtonian fluid, and what level of elasticity, if it's non-Newtonian, that it conveys. So, I'm going to be giving you, as I've said, a complete set of notes for this course, but there are also 2 books that you might find very, very useful, and 2 books that I've referred to for extra reading. The first is called Understanding Rheology by Faith A. Morrison. It was published in 2001, and it's a very comprehensive, if somewhat mathematics-heavy, book around the subject of rheology. The second book is called Rheological Methods in Food Processing by James F. Steffe, and that was published in 1996. And this is a slightly less mathematical analysis, but one that is very, very useful in terms of practical applications and theory applied to those practical applications. So I'll be referring to both of these books throughout the course, so if you can find a copy, that would be very, very useful. So finally, I'd like to make a couple of acknowledgements. I'd like to acknowledge Malcolm, Professor Malcolm Mackley from the University of Cambridge, for first of all creating the predecessor to this course in the first place, and for also giving me his blessing to export elements of his course to the University of Wisconsin for EDP640. And also, I'd like to acknowledge my friend and colleague, Professor Ian Wilson, with whom I used to teach this course at Cambridge, and share many happy memories of doing so. And finally, I really hope that you enjoy this course. I really hope that you get a lot out of it. I hope that you can be enthusiastic about this subject as I am, because it's a really, really interesting subject, both academically but also practically. And hopefully you'll find that a good solid understanding of rheology can start to elucidate some of the things in terms of polymer processing operations that may otherwise seem a little counterintuitive or even a little intractable. So I hope you enjoy the course, and that's it for now.